Okay, hello. So today I'm going to talk about in the case of dynamics of pure rolling. So pure rolling. So in the case of pure rolling, it means it's not slipping nor sliding. So basically, when you in pure rolling, it is a combination of your translational velocity plus your rotational velocity. And I'm gonna use your rotational velocity, but so one of the key things to remember is your rotational velocity is not equal to your angular velocity, but instead is equal to your tangential velocity. So in this case, I'm going to use Vt. So in the case that you have a flat ground and you have a ball that is a wheel that's rolling perfectly on the ground, perfectly round wheel, you have, I'm going to call this the center. You're going to have a translational velocity as it is rolling, pure rolling to the right side from the left to the right. So as it rolls from the left to the right, there is every 1 centimeter that you rotate is equal to 1 centimeter that you translate itself. So basically, you're gonna have as it rotates from left to right, it's gonna move at an angular velocity, and I'm gonna say it's massless, so therefore it doesn't have a inertia. So as it's rotating, it has a tangential velocity of this direction, this direction, this direction, and this direction. And I'm gonna call this your VT, VT, and VT. Now, some of your professors may always have a reference of AN and AT, but they always say V is equal to RW. But the truth is, the V. What kind of V is this? Is this a green? Which green V is this? So this is actually your VT. So in this case, you want to understand the formula is that your Vt is equal to Rw, given that your R is the radius of your circle or your wheel. So what are velocity poles? So velocity poles are these points here. There are four. You can have as many poles as you want, but for this reference, we're going to have 4 poles. And when you have a wheel that's rotating and translating at the same time, the whole mass is translating from left to right. And as it translates, you have the same velocity, translational velocity here. And then you have another translational velocity here, and one here, and one here. Now, if we combine this, both of these velocities together, you get a resultant velocity that moves in this direction. This one is in this direction. This one is standstill, and this one is in this direction. And only because of this, imagine if this point is basically a fixed point. So a fixed point, it rotates. Eventually this circle is going to move here. Yeah, and then it's going to move here. So if you have basically, I'm going to call this point A, point B, point D, and E. So you can say that at point A, your resultant velocity is equal to your Vt plus your V translational. And then at B, you have you kind of have to understand that it's a vector. So you have to know that I'm not going to go with the signs and so on, but you should understand that your V let's call this VB would be equal to, also the same thing, is always your VT plus your V translational. But you need to understand that at D, your V resultant is equal to 0, because it's fixed. Because I mean, it is 0 because the translational and the rotational velocity is equal. If it wasn't equal, then you would have a slipping. It's equal because it's pure rolling. If it's not equal, it means that you will have a sliding or slipping case. So what is slipping? What is slipping and what is sliding? So I will always say sliding means that, imagine you have a hill that is like this, and you are translating faster than you are rotating. So your V is greater than your, in some way you could say your VT that is derived from your your W. And if you were slipping, it would mean, for example, like you are moving, you're rotating faster than you are sliding. So you could say your VT from omega is greater than your translational velocity. Let me just write trans and trans. So yeah, so these are two different scenarios that is often play in the words in the question. So you need to understand this basic idea of velocity poles and the idea of pure rolling and sliding and slipping. Another example of slipping is that, imagine you have a very muddy ground. Imagine you have a very muddy ground, let's say, and then you have a wheel and you are rotating at high speed because of a car. And however, because it's muddy, you're slipping at such a high speed. You're turning at such a high speed, but you are not translating at all. So this is an example of you are slipping. Sliding would be, imagine that you are on ice. Let me see. You are on ice, and as you are trying to run, I'm not very good at drawing, so imagine you are, in some ways you put your feet up and you are trying to push yourself forward at a very high amount of force. However, you're not putting that much force onto the ground, but yet you're sliding really quick. So you're sliding across the ice. So that is my explanation of velocity pole, pure rolling, slipping and sliding.